Good afternoon, everyone. First of all, I would like to thank the organization committee of the conference and Professor Gupta for inviting me today to deliver this keynote called Towards the Internet of Everything with Graphene Antennas and Reconfigurable Intelligent Surfaces. So over the next 45 minutes, I will try to explain our vision that we have at the Universitat Politècnica de Catalunya on the different new applications that nanotechnology can enable in the realm of wireless communications and how to implement them, either with graphene antennas or either through reconfigurable intelligent surfaces, which in the end might have an impact not only in the nanoscale, but also in the macro scale. My name is Sergi Abadal, and I'm a distinguished researcher at Universitat Politècnica de Catalunya in Barcelona, a city that combines modernist architecture, very lively streets, and very friendly people. And I hope you can visit someday. Happy to host you here if you are coming to visit. Universitat Politècnica de Catalunya is a public university in Barcelona with over 30,000 students with a strong focus on science and technology. And also, as a highlight, it's the host of the only supercomputer that it's hosted in a chapel. That's the Barcelona Supercomputing Center supercomputer called Mare Nostrum. So now on to the content of the presentation. So my research center is called Nano Networking Center in Catalunya, which was created with the main goal of carrying fundamental research on nano networking. What we understand by nano networking can be two things. First, communications at very short scales, going down to the centimeter, millimeter, micrometer, or even nanometer scale, and also how communications in general and wireless communications in particular have been impacted by nanotechnology. So without further ado, let me just go quickly over the first part of the talk, which is towards the Internet of Everything. So I'm pretty sure that everyone in this conference will be familiar with Moore's law, which stated that and predicted over the last 40 or 50 years that the amount of transistors that you could fit within an integrated circuit would be doubled every 18 months. This is not a theoretical based prediction. This is not a model-based formulation, but rather an empirical observation that Professor Gordon Moore did 40 years ago, seeing how the trends of semiconductor industry were going. He predicted that the number of transistors would double every 18 months, and he was not wrong over 40 years. So that is well known, and tries to see which are the trends in terms of how the processing speed of different processors can evolve over time. Another trend, another law that it's less known, but it's equally important, is Edholm's law of bandwidth, which is kind of the counterpart of the Moore's law into communications. And he stated that the speed and the data rates of both wired and wireless communication systems would double every 18 months, similar to the doubling of transistors that Moore's law predicted. And this has been maintained for over 20 years or over 30 years now, both in the wired and the wireless domains, although here in this picture, I only show the wireless domains. First of all, the wireless local area network domain, and also the cellular domain, which is on a larger scale. But over time, the different protocols at the wireless LAN and then at the cellular with the second generation, third generation of 4G and then 5G, this trend has been maintained for over 20, 30 years. So it's equally important. And what this law is trying to explain is how the widespread adoption of new technologies on computing and communications are creating new demands, and these demands have to be met in newer generations. And that's why the speeds are doubling every 18 months. Also because there's an explosive growth of data and content now that everyone can take pictures and upload it, create videos, create different content that can be uploaded into the internet. So that creates new needs for higher speeds in the wireless and wired communication systems. But then the question arises, as engineers, as telecommunication engineers, how can we keep the pace set by this Edholm's law? How can we make this thing a reality, right? In wireless communications, there are two ways basically you can do that, right? basically either increasing the spectral efficiency with more complex modulation, so having more bits per second per each hertz of bandwidth that you have in the wireless communication system, or you can increase the bandwidth. So with the same modulation, you increase the bandwidth from, let's say, 10 megahertz to 40 megahertz. You are increasing by 4 times the amount of data that you can transmit at the same time. But well, increasing the bandwidth is not always easy. Assuming that you have the spectrum regulations in place, that you can use the frequency band, you either need wideband antennas and transceivers to achieve that increase in bandwidth. So we need to improve the antennas and transceivers. Either that, or we can increase the frequency. So by increasing the frequency of resonance of antennas, you are somehow also inherently increasing the bandwidth, because generally the fractional bandwidth of a given resonant antenna, it stays over the full spectrum. So if you have an antenna at 1 gigahertz, probably your bandwidth is going to be around 1/10 of that. And if you go to 1 terahertz, the bandwidth is going to be 1/10 of 1 terahertz, which will be 100 gigahertz. So increasing the frequency leads to potential to higher speeds in wireless communications. So if we take the figure that we had before and we try to see which are the frequencies that have been used in different generations, we will see that we start at the lower part of the gigahertz and the microwave bands, and then increasing a little bit the frequency from 2.4 to 5, and also using the band between 3.5 to 5.8. But recently 5G is introducing the new radio that goes at 28 gigahertz. Then wireless local area networks already exist at 60 gigahertz. And the trend is pointing to the use of the terahertz band in the not so distant future to try to keep up with this doubling of speeds every 18 months. So as a result of that increase in frequency, that increase in speeds every 18 months, we have different new paradigms that appear as applications for this wireless communication system. It's not only that we can have more data going around, but also that this opens the door to new applications that were not possible before. Examples could be augmented reality and virtual reality. So connecting to the internet and getting video streamed to your virtual reality headset. This uses a huge amount of bandwidth that you couldn't have before, and now it's becoming a reality. And another problem is latency. Whenever your headset moves, the video that is being reproduced has to move with the headset, so that it needs a very sharp response from the network that also requires very high speeds. The Internet of Things also requires higher speeds in the aggregated amount of the whole network, because everything is going to be connected to it, or everything is connected to the internet. Everything is connected to the internet in a way that in the end the whole network is going to have to support very high speeds to support all this connectivity of all these objects. And then also there's another trend, which is wireless computing. Computers process and move a lot of data within data centers or from chip to chip, and having small antennas that operate at hundreds of gigabits per second would be something very valuable in this different scenarios. So new paradigms beyond the typical wireless LAN or cellular networks arise from these new higher speeds and also more compact devices. So a side impact of increasing the frequency to increase the speed of the wireless communication systems is that the antennas and the analog elements that are needed to realize that communication are also getting reduced in size. That's a very important aspect. You know that the frequency of operation of an inductor or the resonant frequency of an antenna has to do with the length of such antenna or the size of such inductor. So as technology evolves and allows to go at higher frequencies at hundreds of gigahertz, for instance, then inductors become very, very, very small, and also antennas become very, very small. Right? By this inverse proportionality between frequency and size of the antenna, higher frequencies to support higher speeds also mean smaller antennas, to the point that beyond 60 gigahertz, we can start integrating these antennas directly within the chip, right? Normally, lateral dimensions of a typical big chip is around 20 millimeters size, right? So whenever we start going to 60 gigahertz and beyond, we can easily fit antennas within these chips, within these dimensions. Actually, 60 gigahertz antenna is close to 2 millimeters of length. So if we go even higher, we can afford to have even more antennas, right? So at 5G, which is using 60 gigahertz, as I was saying already, these antennas fit on chip, and actually these figures on the right, they are showing that a possible way of integrating antennas within a chip. And the picture in the bottom, what it shows is the typical structure of a chip with the ground plane, then silicon dioxide, and then the metallic layers that are interconnected different transistors. And in this case, these metallic layers can be used to implement the antenna directly within the chip. So we don't need to have one chip to have all the digital baseband computation and then having to go to another component to have the antenna. So this saves space and increases the performance of the communication system. Also, chip transceivers are a reality. So if RF elements that are used to modulate the information are also going at very high frequencies, the size of these transceivers also becomes much reduced. And on-chip transceivers are a reality at very high frequencies already. There's this, I'm just pointing out one example from 6 years ago already at 65 nanometer CMOS, which is a mature technology nowadays. A prototype at 240 gigahertz at very high speeds, 16 gigabits per second, even with a low order modulation, which is not taking very much of the area of a chip, less than 2 millimeters area of a given chip, consuming a few hundreds of milliwatts, which can be reduced depending on what we want to do with this transceiver. But on-chip antennas and on-chip transceivers are already a reality, so we can start integrating them within computing systems or trying to miniaturize the whole thing to reach new applications. Just to give you an example, this is the picture from a sensor mode with a energy harvesting module that can be always on without having any battery, right? And continuously sensing the environment without any kind of battery, just relying on energy harvesting from the environment. This is less than 1 centimeter in length, and when folded is even less than half a centimeter. And if we take a look, there's a Bluetooth antenna and a Bluetooth IC, which is taking care of the wireless part, and this is already taking a few millimeters, right? And only going at 2.4 gigahertz of operation. So you can imagine that if we go at 240, for instance, which is 2 orders of magnitude higher in frequency, we can imagine that 1 or 2 orders of less area can be expected in the antenna, and also a bit less perhaps, but also in the IC. So if you also remove other elements here, like voltage regulators, battery contact, which if you don't want to have batteries, or this socket for external sensors and power access, then we can start thinking about sensor modes which are less 1 millimeter square, 1 cubic millimeter, or even less if you go higher in frequency, and we get rid of non-essential functionalities for that sensor mode. So we can easily imagine many of them being integrated within a capsule that you can ingest and that can go inside your body to get readings of things happening within your gastrointestinal tract, for instance, for one of these possible applications when you downscale everything. So that reaches a point in which we think, okay, so if we take the Internet of Things, in which our everyday things like the TV, like the fridge, like computers, cars, everything is connected, and we take it one step further, and we go to very high frequencies, reducing the size of the antennas to the extreme, we can start thinking of other applications in which the area is one primary concern, like on-chip communication. We can imagine a system in which we have one chip or multiple chips, and we integrate many antennas within those chips, not to communicate with another cell phone or another base station or the access point, but rather communicate within the chip, right? Using all these many antennas to communicate within the chip. And there are many reasons why this is useful for computer architects, but I will not go into detail into that. Another application of that is in-body communication. So wireless communication systems were very invasive if we wanted to implant them or we wanted to have them within the body. But if we start having antennas which are very high in frequency, and that we can put them, many of them, into a capsule that biodegrades within the body, and then or we can inject these nanomachines with antennas, then we can start thinking on nanosensor networks that happen within our body and that take readings of things that are happening within the bloodstream or within our gastrointestinal tract. And that then these readings can go to the internet and then used by your healthcare provider to tell you if everything is well, or you need to appoint for a visit to the doctor to get you tested, right? Another application of having very small antennas at very high speeds would be intelligent materials. So if antennas are very small, that we can be embedded within the threads of a textile or the plants of window blind, or I don't know, other parts that might be interesting to move, to change shape, to change color, to change the appearance or to change the properties of that material, then nano sensors, nano actuators, nano antennas are a very appealing prospect, because they allow to communicate internally within the material, just to coordinate what change of shape, what it means to change of shape, what it means to change the properties of a given material. So if we take a look to the different properties of different requirements in terms of communication that these different applications have, you will see that there are different kinds of requirements in terms of network size, in node density. They change across different applications, from dense to very dense, from communication intensive to very communication intensive, to energy limited to energy actually needing high energy efficiency, to being energy constrained. So yeah, there's a wide variety of applications, but also requirements for these applications. So with this table here, I just wanted to convey the idea that all these different applications were going to have different requirements, and that in the end, with these very small sizes and very diverse requirements, what we will probably need is solutions which are miniaturized and versatile. So wireless communication systems that enable these applications, but that are miniaturized to be able to access within the body, within the chips, or within these robotic or intelligent materials, and also versatile enough to be able to reuse them across systems in the end, to give birth of this Internet of Everything, in which not only everyday things will be connected to the internet, but also within our body we'll be able to communicate, within the chips we'll be able to communicate, or we will be able to communicate within intelligent materials for the next generation of cyber physical systems. So that's a prospect that is very appealing to us at the EntryCAD, and that we keep investigating over the years. So right now I'm posing these questions, or posing this kind of challenge or requirement, in which we need very small antennas and also very versatile antennas. So let me talk you about graphene, and graphene applied to the realm of wireless communication systems, which is exactly what exactly is going to give us graphene. Is this miniaturization and this versatility that we're looking for. So I think it's very appropriate that we talk about it at this time. For those of you that are not aware of graphene, you should, because it has been quite big in the technological domain quite lately. It's the first 2D material that has been theorized and discovered. So the definition would be that it's a 1-atom thick honeycomb lattice of carbon atoms, first theorized by Wallace in 1947, and first isolated 15 years ago, more than 15 years ago, by 2 scientists in Cambridge, André Geim and Kostas Novoselov, which in the end end up winning the Nobel Prize in Physics in 2010 for this isolation and first characterization of graphene. And in the end, what graphene is a very thin layer of carbon atoms. So if you take a pencil and you write with it, the graphite that is left, right, if you peel it many times, this is how Kostas and Novoselov they isolated. If you peel it many times with Scotch tape, in the end, you end up having just a single layer of this graphite, which turns to be graphene. And why is this graphene so important, besides being the first 2D material, is that it was discovered that this 2D material has outstanding properties. So relative to its thickness and size, it's the thinnest material of nature, of course, because it's only 1 atom. You cannot go thinner than that. It's impermeable. It's very strong, stronger than any material for the same relative size. It's very flexible. It's also nearly transparent, but it's a good absorber of light if you need it. It's a very good electrical conductor, and that gives rise to a huge amount of applications in the different domains, and also in electronics and photonics, like what has been laid out and theorized by the Graphene Flagship, which, if you don't know, is a 10-year project in the European Union, awarded by 1,000 million euros. And the goal is to actually make the most of graphene, right? Try to understand which are the properties of graphene and see which are the most promising applications. And in the part of electronics and photonics, many things have been said. Many applications have been proposed in photonics and sensors, graphene sensors, flexible displays, and so on and so forth. But what's interesting for us is wireless communications and how graphene can be used to improve wireless communications. And that's what I'm going to talk about now. So among all these properties that we were mentioning, one of the properties that is relevant to this talk today is that graphene has excellent conditions for the propagation of surface plasma polaritons, otherwise known as plasmons for short. So these plasmons, the surface plasma polaritons, they are electromagnetic waves that happen to appear at the interface between a metal and a dielectric. And a metal can be graphene, or it can be any other metal. Gold has also supports plasmons, although they do it at different frequencies. And what's important in this slide is that these plasmopolaritons are slow waves. What this means is that their propagation through a surface is going to be slower than with the propagation of electrons through a surface, right? Through a metal in a regular surface. So what this means is that the special relation between in an antenna made out of graphene that supports SPPs is going to change. So this is very important for us for some reason that we're just going to talk about now. Beyond that, the particularity of graphene with respect to SPPs, as we said, gold and other metals, they also support SPPs. But the important property is that graphene supports SPPs in the terahertz band. Remember, 1 terahertz is 1,000 of gigahertz. So when you increase frequency from 2.4 to 60 gigahertz, the next step is going dipping into the terahertz band, dipping into 100 gigahertz, 300 gigahertz, or 1,000 gigahertz, which is 1 terahertz. So the important property of graphene is that it supports SPPs in the terahertz range, while gold and other materials, they support it in the infrared. So they only can take advantage of SPPs in their infrared. And we want it in a slower frequency, which is terahertz, which is good for us. Beyond that, another property of SPPs in graphene is that these SPPs are tunable. So by changing the voltage, changing the bias voltage or the biasing of this graphene, you are able to make these SPPs faster or slower, appearing at different frequencies. So that means that the SPPs are tunable, which has very important properties for the creation of antennas, which is what we're going to talk about now. So in all these applications in which you have very small, in which you need very small antennas, perhaps going down to the micrometer range, if you take a metallic antenna and you try to just downscale a metallic antenna to hundreds, tens, or a few micrometers, what will happen is that by this inverse relationship between the length of an antenna and the resonant frequency, an antenna of a length of a few tens of micrometers is going to radiate or resonate very easily at a few tens of terahertz, so very quickly going into the infrared. While our idea is to go to frequencies which are closer to 1 terahertz, closer to 300 gigahertz, right? So yeah, if you want to have very small antennas, what it happens is that it will go to the optical regime, which is not very good for wireless communications, right? So that's not it's not a good news for nano sensor networks or any other applications that require antennas in the micrometer range. But if you apply this same reasoning to graphene and you check which is the resonant frequency of a graphene dipole over a given substrate by this action of the SPPs, it's not only that that this graphene antenna is going to resonate at a lower frequency, which means that for a same frequency, the graphene antenna is going to be way smaller, but also that this relationship between the frequency and the length is not going to be inversely proportional to the length of the antenna, but inversely proportional to the square root of the length of the antenna in a way that you will be able to scale better to lower sizes and in the end lower frequencies. So in the end, what we obtain from this theoretical analysis of modeling the dispersion relation in graphene is that a graphene could enable antennas which are 1 or 2 orders of magnitude smaller than metallic antennas for the same frequency or the same size. So knowing this, what we did is start to investigate if this is real, at least from the simulation perspective. So we took a well-known electromagnetic full wave simulator and we implemented a graphene antenna in that simulator. And what we implemented is a very simple dipole with a gap and then a photoconductive source in between, everything on top of a substrate, and having 2 biasing lines on the exterior of dipole arms to provide the DC biasing that graphene needs, right? What we did is to take that scheme and change the size of the graphene dipole, change the size of the arms, and compare it with exactly the same antenna with the same gap made out of gold, right? We observed that the frequency of resonance that you can see in the picture on the right between graphene and gold, there's almost more or less 1 order of magnitude reduction between the resonance point of a gold antenna and the resonance point of a graphene antenna for different sizes, right? So that leads to confirm that there's indeed miniaturization when we try to simulate a realistic type of antenna. What we also did is to change the voltage that we apply for the biasing, which in graphene, what this means is that it changes the chemical potential of Fermi energy, which in the end ends up being a physical attribute of the energy that this graphene is containing. So we did that without changing at all the size of the antenna. So we were only changing the voltage without changing the dimensions of this antenna. And what we observed is that the frequency of resonance, as you see on the figure on the right, the frequency of resonance when we change this voltage or this chemical potential changed from 1.5 terahertz up to 3 terahertz, which means that the frequency of resonance has doubled without changing at all the physical dimensions of the antenna, which means that the antenna becomes tunable. So we can change the frequency of operation of the antenna by just changing one voltage. And moreover, we observed that when we increase this Fermi energy, we would increase the efficiency of the antenna. So what this means is that there's a trade-off between miniaturization and the efficiency of the antenna. The more you miniaturize, the less efficient is your antenna gonna be. But in the end, well, if you need the antenna to be very small, maybe you can trade off this efficiency. But beyond that, we observed in the end that the antennas would be miniaturizable. And also that we would have this kind of tunability, which also means switchability. So if your system is operating at a given frequency and you change that, you tune the frequency out of that frequency, then your antenna is like not there anymore, right? So you can apply this to switch on or switch off your antenna from the perspective of being electromagnetically seen at a given frequency. So we thought, why not try to take advantage of this tunability or switchability to obtain more complex antennas that could benefit from that. So we started trying to see how those antennas can try to approach something that can be experimentally validated. And we kind of designed a test bed in which people could replicate in real life to actually experimentally validate if graphene antennas would radiate or not. We're still in the process of validating that, but we are quite near, I would say. So then beyond that, we started like looking at different alternatives on how to exploit this tunability or switchability of the antenna to try to have new designs of graphene-based antennas that would be reconfigurable, miniaturizable, and so on and so forth. This is one example in which we coupled a graphene antenna to a dielectric resonant antenna so that changing the Fermi energy, changing the voltage to apply to the antenna, the DRA would be tuned in or tuned out of the antenna to increase the gain of the antenna. So in the end, that means that the antenna could have different radiation modes, as you can see in the figure on the middle. There are 3 types of modes, and the different modes have different gains at different frequencies because you are activating the DRA mode or the other modes. And on the picture below, you can see the different radiation patterns for the different modes. The mode more on the left was radiating thanks to the dipole, so it's radiating well around the dipole in the horizontal dimension, while changing the voltage would switch on the electric resonant mode. And as you can see on the picture on the bottom right, now the antenna is better suited for vertical radiation. So by just changing one voltage, you're switching on or switching off the horizontal or vertical radiation mode, changing also the gain of the different modes of the antenna. So that's one way of using the tunability of graphene. Another example of this tunability used in more complex antennas for systems that are a bit more complex is this Yagi antenna based on graphene, in which we used a graphene for both the dipole that is actually radiating, the directors and the reflectors and the directors of the radiation, which are typical in Yagi antennas. So by changing the voltage of all these elements, we can make them inside of the antenna or tuned out of the antenna so that we can activate the YAG-UDA mode, or you can deactivate it in a way that by also changing the voltage of the driver, of the antenna driver, you can also change the frequency. So what you can see on top right is how combining 4 of these YAG-UDA antennas and changing the voltage of the different elements, you can have directive radiation north, south, east, and west, depending on what are the needs of your system. So by changing voltages, you can just have this reconfigurability. And on the figures on the bottom, what we observe is that we can also have joint frequency and beam tunability, in the sense that we can have in this antenna at the same time changing the direction and also changing the frequency. So beyond that, we started investigating how we can generalize this effect of the YAG-UDA antennas in arrays that are trying to radiate in any direction with many different frequencies. Is that what metasurfaces allow you to do? So we designed a unit cell with graphene that by changing the chemical potential would have different amplitude and reflection phases, which in the end is what you need to design metasurfaces. I will not go into much detail, but just let me tell you that this reconfigurability was inherent to graphene without needing any other materials or components like pin diodes, which is used in reconfigurable antennas in real life. And by using that unit cell, replicating it many times to create a metasurface, we demonstrated that we can have terahertz beam steering. We also demonstrated that we can have terahertz near-field communication in multiple points in space. So we were demonstrating that actually graphene opens the door to from very simple to more complex antenna systems, which are very compact and very much reconfigurable, providing the versatility that novel nanocommunication systems require. And just to mention, this WIPLASH project that we are now involved, what it proposed is to try to use that in on-chip communications, right? To try to integrate graphene antennas within the chips of a computing system, and by virtue of this miniaturization, we will be able to actually integrate arrays of these graphene antennas. And actually, thanks to this tunability and this versatility, we can kind of create steered beams around the computing package and actually change frequencies. Like we can create multiple frequency channels and multiple spatial channels in an environment that requires a lot of data movement over time. So in this, just giving you a little bit more insight on this project, the targeted breakthrough of this European project is to actually experimentally validate that these graphene antennas actually radiate in the terahertz band with some miniaturization and some tunability. And we are very interested in it because going to the terahertz band gives you more bandwidth for this application, which is very much data hungry, because these antennas are much smaller than metallic antennas, and they of course take less area in a place where the area is pretty much constrained, and they are uniquely tunable to provide this possibility of having multiple bands and multiple beams across the system. So just to close this topic, of course, this leads to many different challenges and many questions, like how do we integrate these graphene antennas with the transceiver circuits and the processor cores of our computing system? How is the wireless channel at terahertz frequencies within the computing package? So how do the terahertz waves propagate through the package? Is there going to be a lot of path loss? No, and that's a question that needs to be answered. How do we manage the many frequency and space channels that now become available thanks to these graphene antennas? How we take advantage of these antennas from the architecture perspective? So how do computer architects take this new communication pattern and redo the architecture so that they can go faster? These are open questions that we try to answer in WIPLASH. Okay, so with that, let me close the chapter of graphene antennas, of nanosystems, of systems that require very small antennas. And now let me move back. Let me take a step back and move to the macro world in a part that I call reshaping our wireless world with reconfigurable intelligent surfaces. So as I was saying, let me take one step back to these applications in which they are not necessarily in the nanoscale, but require very high speeds that require in the end going to the terahertz band, going higher in frequency. So remembering that at Ohm's law of bandwidth for enabling all these applications, we need to go higher in frequency. Let me just try to burst you a bubble, right? Going higher in frequency is not always for free. It has some technological requirements that are not easy to obtain. Having circuits that operate at terahertz, it's not very easy. But beyond that, just focusing on the communications, this going higher in frequency and having higher bandwidth does not come for free. And for that, we take a look to the physics equation, which relates which calculates the path loss, calculates all the losses that go from the transmitter to a receiver of a wireless communication system. If we take the physics equation, which is assuming that we have resonant antennas, physics equation tells you that one part of these losses that happen between the transmitter and receiver are related to the frequency. So the higher is the frequency, by virtue of this last term, the higher is the frequency, or in other words, the smaller is the wavelength, the more losses you would have between transmitter and receiver. That means that more power needs to be put into the antenna to actually achieve the bandwidth that you want. So you either reduce the distance that you want to transmit, or you go into other things. You try to increase the gain of the antenna so that you can counteract the fact that you're losing more energy, right? But no, it's not only that, it's also that beyond these higher spreading losses, which is what we were talking about, when you start going to the terahertz band, everything can be a blocking element, right? So going through walls is not that easy anymore. Going through trees, going through people, it's not easy anymore, like microwaves. So everything can block your signal. There's also the effect of molecular absorption, which adds to the noise and adds to the attenuation of your signals. So what this means is that in the end, if you don't do anything additional, the terahertz communication is going to have very, very short range. So we have to try to see how to combat this problem of having a very short range. The problem comes from the fact that the channel is your enemy, that the channel is the cause of all these spreading losses, of this non-line of sight propagation, which is hard to provide, obstacles, adding scattering, adding reflection that might be harming your signal, molecular absorption. So these are all problems that you cannot avoid because the channel is given. The channel is your surroundings, the city that's surrounding you, the office that you are in, and the reflection. You cannot control the size of your surroundings, at least not usually, right? So always we have considered the wireless channel to be a given that you cannot control, and it's going to harm you. But what if we are able to make the channel your friend? So what if we can control the direction of reflections? What if we can coordinate multiple reflections so that they constructively interfere at the receiver? What if we can block harmful signals? What if we can collimate beams so that we don't lose energy being spread around? So what if wireless environments can be now programmable and can be put in within the optimization loop of the network? What if this happens, right? So that would be great. That would be great. That would solve lots of issues of going to the millimeter wave and terahertz frequencies, because non-line of sight wouldn't be a problem anymore, because you would be able to actually direct radiation to the receiver in a sort of virtual line of sight always, right? And you would solve many of these problems. But how do you implement this? How do you make the channel your friend? How can you control the reflection? How you can control these kind of things? Well, the literature is now full of these proposals of large intelligent surfaces, reconfigurable intelligent surfaces, intelligent reflective surfaces, software-defined metamaterials, hypersurfaces. All these names refer to something which is very, very similar, which is a reflector with some intelligence. All these new proposals, what they do is to have a reflector with some intelligence and some programmability to provide you with this control over the electromagnetic waves. So let me just very quickly go to what we mean by reflectors and what we mean by intelligence. What we mean by reflectors are two things, right? One thing could be a reflect array. So you know that an antenna arrays, when you provide signal to an antenna array, you can control the direction by just controlling the phases that you have in that array, right? So you can do something similar as a reflect array. So without having an antenna near, you just put a reflect array on a wall, and you can control the direction of the reflection rather than the direction of the transmitted signal. You can control the reflection. So you can think of reflect arrays as an array of passive antennas that can help you direct the information where you need, right? So instead of having this kind of complex antennas, which you will still need for massive MIMO and the like, you will have intelligent reflectors around your rooms or around the city that will be able to direct the information where it's needed. But beyond reflect arrays, which would be this kind of passive antennas, There's another concept which is even more stronger than it's even stronger than that, which is the concept of metasurface. A metasurface is a planar structure composed of arrays of sub-wavelength elements called unit cells that enable unprecedented control of electromagnetic waves. So in essence, a metasurface is a very strongly coupled, dense array of antennas, if you will, right? And if it's passive, it's a passive array of antennas. But the idea here, the key element is that they are sub-wavelength elements, that they are very closely integrated so that they are more compact than a regular array. And beyond being more compact, they are also more powerful in controlling the electromagnetic waves. Why? Because with metasurface, you can control not only the absorption, so you can absorb electromagnetic waves in a new way, but also you can control the direction of reflection. So if you have a planar wavefront, you can control that the same planar wavefront goes to a different direction. And you can also control the scattering. So how a planar wavefront is converted into an arbitrary wavefront and an arbitrary scattering pattern. So by means of these properties, many different elements that use metasurface have been appearing recently in the literature. You can implement planar lenses that control when you focus your energy, polarization converters, optical mixers, absorbers, non-reciprocal devices, retroreflectors, antennas, and so on and so forth. So by means of this metasurface that allow to control electromagnetic waves in a way that you could not before, new applications have been arising, like better solar cells, better imaging systems for healthcare, better ways to avoid radars, and so on, better ways of steering beams towards the destination in communication systems, ways to actually, if you can engineer the wavefront, you can create holograms. That's a new application of metasurfaces, or random scattering, right? So if you want to go under the radar, one thing that you can do is to create a reflection which is randomly scattered so that the radar will not be able to detect. So that's another application of metasurface for arbitrary scattering engineering. So if we go to the wireless communication systems, which is my main topic today, all this control of reflection, absorption, and scattering has lots of applications. If you're able to control that, you're able to direct energy to the destination. You're able to block users which are not allowed from the physical layer. You can actually have multicast to multiple directions thanks to these reflective surfaces. You can reach destinations that you could not reach before. You can focus energy if you want to just reach one user with a higher efficiency and so on. So there are many things that can happen that could not happen by just having sophisticated antennas in the millimeter wave and terahertz bands. So that's what reflectors can do for you. And now let's talk about intelligence. How do we actually allow these reflectors, this metasurface, to be controlled from the outside? How can we tune the response of these reflectors so that we can direct the information from one point to the other to change from absorption to reflection and so on and so forth? How's this intelligence? So for this, we need to go to the basics, right? First, metasurfaces were created just being static, just being passive, right? So we design our metasurface in a way that you cannot do anything else than what it was designed for. So the different elements, they are handcrafted to have the specific response that they needed, and they are put together so that the metasurface is gonna, let's say, steer the beam to a given particular direction that they cannot change over time. That's the beginning, the first generation of metasurfaces. But then we started to integrate, so the community started integrating tuning elements within these metasurfaces to change the impedance of different of these unit cells that compose the metasurface, so that you could start thinking of having tunable metasurfaces. So metasurfaces that can change the functionality, or they can change the direction of the reflection, to give you an example. These were proposed at the microwave, at the millimeter wave, and also the terahertz band, as you can see from left to right in this figure before. Then we observed that integrating tuning elements, it's not enough, right? You need something to control these tuning elements. And people started to propose to have an FPGA on the backplane of the metasurface and connect this FPGA to all the different tuning elements of the metasurface. So the FPGA became kind of a interface, a programming interface to the metasurface. So giving codes to the FPGA and the FPGA transmitting them to the different tuning elements the functionality of the metasurface would change either by the direction or either directly from the functionality from beam steering to another functionality that we might want to have. So then the metasurface starts to become something that can be externally and digitally controllable, which is an important step towards these reflective intelligent surfaces. So with this idea of externally and digitally programmable metasurface, things started to explode in the 5G and 6G domain wireless communications. So people started to think, okay, what can I do with reflective intelligent surfaces? Can I have hybrid precoding design? Can I have index modulation? Can I have indoor signal focusing? Can I have unmanned aerial vehicle communications aided by these surfaces? Can I do indoor beaming for virtual reality? Can I do weighted sum rate maximization of my system? Can I do energy efficient multi-user MISO? Can I do wireless power transfer beyond max joint encoding? NOMA, two-way communication, so simple beamforming at terahertz. So many things, and they are real concepts found in papers talking about reconfigurable intelligent surfaces. Many things happen in 5G and 6G research related to this RIS kind of concept. So in our work, we try to go one step further, right? Trying to provide the vision of nanonetworking in this world of reconfigurable intelligent surfaces. And we start thinking about what if we can scale that to higher frequencies, to higher extents, to higher densities? What if we can have space-time reconfigurability? What if we can host multiple functionalities within the same metasurface? What if we can interconnect multiple of these metasurfaces to have a joint optimization of the channel? What if we can have autonomous and learn intelligent metasurface in the sense that they can learn from the environment and adapt to the environment? What if we have resilience in these metasurfaces? So if we partially destroy them for whatever reason, they can still work. What if we have ultra low power and they can perpetually operate only with energy harvesting? So what if all these things happen? And this what led us to think about hypersurfaces as programmable, autonomous, intelligent, and interconnectable metasurfaces, which have the communications and control integrated within the surface. So we're not using FPGAs anymore. We integrate everything within the metasurface to provide connectivity and to provide controllability. This is the concept of hypersurface, in which the unit cells, they have a chip on the back. All these chips are connected to a given gateway that connects to an access point. And the access point can send commands to this bridge, to this gateway, that will enter the metasurface, and the metasurface will change the functionality or the direction or whatever. So we have an API, a programming interface, that from the internet you can control this material to change the reflection, to change the absorption, the polarization, and so on and so forth from the outside. And what enables this is this intra-hypersurface nanonetwork. We have this nanonetwork of chips that control this metasurface. So this is where the nanonetwork paradigm has a role in this new reconfigurable intelligent surface kind of idea. Beyond that, the fact that we have a gateway to this metasurface allows us to interconnect multiple of these metasurfaces through this gateway, right? So this metasurface can share information of location, of channel state information, to try to jointly optimize a given channel. So that's very important also to take this idea further. Okay, so this idea is great, right? But there are three questions that we wanted to answer in our research. So in our applications, whatever application that might be, how large should the hypersurface be, right? Should be as large as possible, but also as small as possible, because larger things generally are more expensive, right? So which is the minimum amount of unit cells that I need to put to actually cover a given application? Second, how do failures affect the hypersurface when we deploy it, right? And things happen to this hypersurface. Can we still think that after 5 years the thing will still work as if it was new? So how errors do affect the hypersurface? And finally, how fast should the internal chips of this metasurface be, right? How many instructions per second do they need to support the changes in speed, changes in direction, changes of functionality that my wireless communication system requires from the metasurface? So to start doing that, we expressed the programming of the metasurface as a kind of a pseudo-mathematical notation. we have an electromagnetic wave with a given frequency, amplitude, polarization, and direction that impinges on the metasurface, which has a given amount of unit cells with a given amount of unit cell states, that the phases that we can apply to these unit cells, and a given metasurface size, how many of these unit cells we have, right? And in the end, we also have an application, a functionality, a given set of specification in speed, in performance that this metasurface has to provide, right? So given the wave and the metasurface, to cover a given application, which is my metasurface, how does my metasurface has to be, right? So that's what we will try to solve, right? Finding which is the number of unit cells, the size of the metasurface, and the number of states of this metasurface that need to be provided so that we can service a given functionality with a given set of performance metric. This is a very complex inverse problem, how to design a metasurface that gives birth to a given application. That's a very complex inverse problem, but we can help giving design guidelines. So what we did as a first contribution is a scalability analysis of metasurfaces. So we basically took a unit cell performance model, we integrated it into a metasurface model, and then for a given application, we encoded the metasurface to do whatever the application needs to do, and we calculated the performance metrics of that functionality. Let's say that we encode the metasurface for beam steering, so we calculate which is the gain, which is the beam width, and so on, to see how the metasurface is doing. And we repeat that analysis for many different number of unit cells, size of unit cell, and the number of states that these unit cells can provide. So to see if the performance scales well or not. Right? We simulated unit cell model and we integrated that into a more complex analytical model, and we started extracting results like the directivity at a given direction that we wanted to steer the beam. So we can see from left to right, increasing the number of states, and in each of the figures from left to right, having bigger unit cells, and from bottom to top, having more unit cells, or having bigger metasurfaces. So we observed that, of course, having the bigger metasurfaces with the smaller unit cells was better, right? And that having more states was always better. But we can start seeing which are the trends of scaling and which are the points at which, okay, if my directivity is good enough with 15 dBs, when I can stop being, which is the density and which is the size of the metasurface that I can afford, right? And the same happened with a second metric, which is the deviation from the targeted steric angle in degrees. So again, we see that bigger metasurface, with more dense unit cells, which is top left on each of the figures, is better, right? But at some point, we don't care about having bigger metasurfaces, because this is not gonna provide improvements in the deviation between the actual beam and where we wanted to point the beam. So that means that we can have a trade-off analysis between the cost of the metasurface and the actual performance that it provides. So this scalability analysis was trying to provide the guidelines in this regard. Then the second contribution was an error analysis. So what happened? So this hypersurface, because it integrates electronic circuits, it integrates communication circuits, it's rather complex, right? And things can fail when they are more complex. Things tend to fail because one connector is not well put, because there is misalignment, because one chip fails, because things happen, right? So in another direction, we also wanted to see what happens if we switch off a given amount of unit cells, or a given amount of chips, to save power consumption. So see what happens and how the performance of the metasurface would degrade, if that would degrade gracefully or not. And just we were not clear on how these things would affect the performance of the metasurface. So our contribution was defining an error model on what things can happen and what impact can have on unit cells or in the distribution of these failures over the metasurface, and see how the performance, like the beam steering, the directivity in a given direction, would be affected by these errors. So we started by this definition of the types of errors that can happen in the circuitry of a metasurface. And just to give two examples, so a deterministic type of error, we consider that if you destroyed a given unit cell, or you destroy a given area of the metasurface, and you make a hole out of it, then the response is going to be deterministic. There's going to be full transmittivity, because you're not receiving it anymore if you make a hole over a metasurface, right? So that's a deterministic behavior of an error. But another error could be staggered state, in which imagine that we power off a chip of the metasurface so that you cannot change anymore the state of a given unit cell, right? So the unit cell can get stuck to the last state that it was given. So we can imagine that those unit cells will not change the state anymore, and they will get stuck to the previous unit cell state. So if the metasurface needs to change the state, those unit cells will not change anymore. So that becomes an error if the state that you are stuck at is not the state that you're supposed to be at that point in time. And we also made a hypothesis on the distribution of spatial distribution of these errors over the metasurface. For instance, if errors are independent because they have different sources, you can expect that they're going to be independently placed on the metasurface. While if you make a shot over a metasurface, you can expect that the errors will happen around a given area of the shot. So that's also another different distribution in terms of spatial distribution of the errors, which is clustered, right? So we just hypothesize different types of distribution of errors and different types of the impact of errors on a given unit cell. And then we introduce that in our methodology into our semi-analytical methodology, and we start investigating how the errors would affect the metasurface performance for different percentage of errors and different combinations between the distribution of errors and the type of errors. For instance, from top to bottom, you can see the impact of, from left to right, you can see the impact of increasing number of errors, 15, 30, and 45 amount of unit cells that are faulty, and you can see that this beam that is steered to a given particular direction starts being reducing the directivity and start giving rise to side lobes which are not wanted, right? And you also can make the comparison between the top row and the bottom row, which are different types of errors and their distribution. And you can see that different types of errors and different distributions can give you different effects. So if you take a look at the 45 case, the one on the top is giving you much more interference than the ones are on the bottom. So different types of error can affect you differently. So you might need to have different protocols in place when errors affect your hypersurface. And again, different types of errors become more or less harming to your case. The case on top is a very good one, in which you have independent and out of state errors. So the errors are kind of scrambled over the metasurface that barely affects your response, even if you have 45% of errors. So that's pretty much a good result. But of course, you cannot control how the errors happen, right? But if the errors are independent for whatever reason, then having many faulty unit cells don't have to actually mean that your functionality is removed. And then the third contribution, very quickly, what happens internally, right? Internally, you have many chips that they have to change the state of the unit cells, and they have to communicate to neighboring chips to tell them, okay, now I changed to this state, you need to change to this other state. So what we wanted to see is in different use cases in which there's a person moving across the room or within the city, which is the speed at which we need to change the state of the metasurface, and how that translates to the internal workload of the nano network within the chips of a metasurface. So essentially, we simulated movement, and then we simulated which is the change of angle of the metasurface to follow that user, to track that user, and then we simulated how that would translate into the internal communication of the metasurface. And we observed, for instance, in this example here, we have 5 metasurfaces, 5 hypersurfaces, and we see that over time, depending on how the user moves, there's going to be more or less transmission, or more or less internal communication requirements from the different hypersurfaces, always in the range of megabits per second. So internally, your hypersurface needs to process things on a megabit per second scale. So the interconnects, the chips should be able to work at those speeds. Of course, whenever we solve all these issues, new open challenges arise, right? How do we share the hypersurfaces among multiple users that want to impinge into the same hypersurface? Do we do it on time, frequency, code, right? How do we orchestrate exactly multiple hypersurfaces for large problems, joint optimization of a given channel? Can we make the hypersurface autonomous and perpetual thanks to energy harvesting? So how can we make that happen? Can we apply machine learning techniques to make the hypersurface adaptive to multiple complex contexts and functionalities without having to redesign it, right? Without having external control of this hypersurface, just by their internal intelligence? So these are very interesting questions that might give you more results. So after these challenges, I don't have anything else to say rather than to conclude the talk with these conclusions. So modern times are bringing an insatiable appetite for bandwidth, requiring the migration to higher frequency bands in wireless networks. This opened the door to new paradigms such as the Internet of Everything, everything connected at very high speeds, but also brings new challenges. In the micro scale, how to design miniaturized and versatile antennas, and in the macro scale, how can we counteract the fact that the channel is much more hostile due to the free space path loss, blocking interference, and so on and so forth. So in response of these micro scale challenges, graphene antennas, they are a very promising alternative due to this miniaturization and tunability that they provide. And in response to macro scale challenges, this reconfigurable intelligent surface paradigm is already a reality and also bringing many new challenges from the perspective of adaptivity, interconnectivity, and autonomy. But overall, for me, or at least in EntriCAD, two very interesting aspects to research over the years. Without anything else to say, just acknowledge the teams of the VISORSURF project in which we worked on reconfigurable intelligent surfaces, and the team in the WIPLASH project in which we work on graphene antennas for next generation computing systems. Thank you very much, and now I'm open for questions. Thank you.